Okay, so in section 6.3 we start talking about the further developments of the quantum theory. So the first stage in this process was when people started to consider that if light sometimes is best described as particles, perhaps sometimes particles or matter are best described as waves. So the first person to start thinking about this was a guy called Louis de Broglie, who was a French prince, and he thought exactly as I described, that if under some circumstances light is best described as a particle, perhaps there are some things that are readily explained if we consider matter, i.e. things like electrons, to have wave properties. And he recognized that if electrons behaved as waves, this would account for the quantized energy levels proposed by Bohr. And the reason for this is that if an electron had wave-like properties, then it turns out that its orbits would be restricted to sizes that corresponded to multiples of a whole number of wavelengths. And I'll show you why that is. So here's what we're visualizing here is the electron. Now we're thinking of it as being a wave rather than a particle, and so it's a wave that's in the form of a circle. And what Louis de Broglie realized was that it has to be a whole number of wavelengths that make up this circle. That is, the circumference of the circle has to equal an integer number of wavelengths. And the reason is, if it doesn't, what happens is when you go around again, you start getting troughs meeting up with peaks, and what you know will happen then is you get what we call destructive interference, and our particle would disappear. So by recognizing that if you treat the electron as though it is a wave, and when it's in an orbit, it's a circular wave, and then what de Broglie found out is why only certain energy levels, certain radii orbits are allowed. Now he went a little bit further than this, and what he did was he combined Einstein's famous equation E equals mc squared, what we call the mass energy equivalence equation, with Einstein's equation for the energy of a photon. But he said, if this is a particle, we don't talk about the speed of light anymore. What we're going to talk about is its velocity. So he just substituted velocity in there, and when you combine these guys and reorganize and solve for the wavelength, and you can do that if you want, you end up with this expression, which allows us to solve for what we call the de Broglie wavelength of a particle. So what we're going to do now is look at what the result is when we apply the de Broglie equation to an ordinary object moving at an ordinary speed. So it says, what is the de Broglie wavelength of a 142 gram baseball thrown at 44 meters per second? And this corresponds to a baseball moving a sort of a little over 90 miles per hour, which is a pretty quick baseball. The thing about using the de Broglie formula is you do have to make certain that your mass is in kilograms, and the reason for that is it's related to how the joule is defined, which appears in Planck's constant. So we're going to have to express this guy in terms of kilograms. Other than that, it's pretty straightforward. So the wavelength is Planck's constant divided by the product of the mass and the velocity. So 6.626 by 10 to the minus 34. And I'm going to write this in terms of the base units, kilograms, meters squared per second, divided by, make sure you put that product in parentheses, 0.142 kilograms times 44.0 meters per second. So one of my meters is going to cancel, my kilograms is going to go, my per seconds are going to go, and it's going to give me a wavelength in meters. And I put that into my calculator, and I see that it is 1.06 times 10 to the minus 34 meters. Now remember that atoms are around about, just a generic atom, 10 to the minus 10 meters across. So this wavelength is extremely small, smaller than subatomic particles. So yeah, it's really small. So for ordinary particles traveling at ordinary speeds, the de Broglie wavelength is insignificant. It's so small that we don't observe any of the wave properties of our particle. However, when you go to a really small object like a subatomic particle, or even an atom itself, then the wave characteristics become very important. The wavelengths get a lot bigger, and the wave properties of the particles start to dominate. So what we see is that matter, just like light, has both wave and particle properties. This is called wave-particle duality. So let's do a de Broglie wavelength calculation for a subatomic particle and see what we get. So we know the formula. The wavelength is equal to Planck's constant divided by the product of the mass and the velocity. We have to keep our mass in kilograms, which is fortunate because this time they gave us the mass in kilograms. So this particle, which is an electron, is moving at 10% the speed of light. It's really common to give the velocity of a particle in terms of a fraction or percentage of the speed of light. So we'll go ahead and do the math. 6.626 times 10 to the minus 34 kilograms meters squared per second divided by, and then the mass there, 9.11 by 10 to the minus 31 kilograms. And then our 10% is 0.100 times by 3 by 10 to the 8 meters per second. So kilograms is going to cancel kilograms. One of my meters will cancel. My per seconds cancel. It gives me my wavelength in meters. And what does it turn out to be? 2.43 by 10 to the minus 11 meters. So what we see now is that this is sort of like on the scale of the size of an atom. So we can't just ignore the wave-like properties of an electron in an atom because the wavelengths are similar in size to the size of the atom, and these wavelengths become, these wave-like properties become significant and important. So what comes out of this is a recognition that perhaps we don't really quite know where the electron is as well as what we think we do, because a wave is spread out over a region of space. In our case, it's in a circle, right? So particles have a distinct location and are said to be moving at a precise measurable speed, but waves are more diffuse and are spread out across a region in space. And, it just becomes sort of, where is this wave becomes becomes quite a deep question. So if matter has both wave and particle properties, when you do the math, it turns out that there is a limit to the degree of certainty with which you can know the position and speed of your particle. And this is summed up by a property called the Heisenberg's uncertainty principle. And what it states is that the product of the uncertainty in a particle's position with the mass multiplied by the uncertainty in the velocity is always greater than or equal to Planck's constant on 4 pi. So I want to just point out that the product of the mass and the velocity is known as the momentum, often given the symbol P, and so you will see sometimes people will express this in terms of P, and I think your book does that. Okay, so let's have a look at a Heisenberg uncertainty type problem. So it says, what is the minimum uncertainty? So we're solving for delta x here. In the position of an electron, it gives the mass, thankfully in kilograms, moving at 4 by 10 to the 6 meters per second with an uncertainty of 2% in its velocity. So this 2% here represents my delta V. So delta V is going to be 2% of the velocity, okay? And that will be in meters per second. So now we just got to solve. So delta x multiplied by m delta V is always greater than or equal to h on 4 pi, which means that delta x is greater than or equal to h on 4 pi m delta V. So I've got to put all of that into my calculator. I'm not going to put all the units in because I would run out of space. When I put that into my calculator, delta x ends up being 7.23. That's not a 3 at all. 7.23 by 10 to the minus 10 meters. So that's interesting. This has an uncertainty in its position of several atom widths. You know, this is like several times the size of a hydrogen atom. So this uncertainty in the position is significant. We actually kind of, you know, we're really limited in where we know where this particular electron is. So that's kind of cool. So at this point, we have firmly kind of established the idea that sometimes matter has wave-like properties, and those wave-like properties can actually dominate for very small particles like electrons. So a guy called Erwin Schrödinger took this and developed what we have now, which is the most sophisticated quantum mechanical model, which is based on what is described as Schrödinger's equation. Now, Schrödinger was a kind of an interesting guy. He had a very unusual personal life. He's probably most famous, though, for his thought experiment, which is referred to as Schrödinger's cat. And what Schrödinger realized is that when we get to these very small particles, that the only way that we can describe them is via statistical models, and sometimes these statistics kind of lead to conclusions that are slightly illogical, or not what we're used to thinking about in everyday life. And a good example of this is Schrödinger's cat, which seems to be stuck somewhere between being alive and being dead. So in the Schrödinger's cat thought experiment, you have a crate which is divided into two compartments, and there are holes in the barrier that allow the two gases to move between the two compartments. On one side of the crate, you put a cat. On the other side of the crate, you have a fairly elaborate setup. What you have is you have a Geiger counter, and it's connected to a device that releases a lever. And if the lever gets released, a hammer swings down, and it breaks a vial containing a poisonous gas. So if the Geiger counter goes off, the hammer falls, the vial breaks, the gas gets released, and the cat dies. Now, what determines if the Geiger counter goes off or not is a piece of radioactive material. And this material, on average, releases a radioactive particle once an hour, but it's random. So over the long-term average, it releases one particle an hour. But sometimes it releases like 3 in a row and then nothing for like the next 3 hours. So, you know, on average, it releases a particle every hour. So what Schrödinger asked us to think about is, what if you put the cat in here, nailed the lid on the box, and then left this set up for half an hour? How would you describe the state of the cat, considering that you can't look at the cat? Well, you'd have to conclude that the cat had a 50% chance of being dead and a 50% chance of being alive. So the only statistical valid way of describing the cat is saying that it's half dead and half alive. Okay, so when we're talking about electrons in atoms, it's a little bit like that. The electrons are in a box that we can't see with our senses. We can't do anything to trying to observe them, or we're going to make them move. So we're going to develop statistical models to describe where the electron most likely is. And every now and then these models are going to seem slightly illogical, but that's the best that we can do. So according to the Schrödinger equation, you can calculate the energy of an atom or an electron in an atom. And what the Schrödinger equation says is that if we have this thing called the Hamiltonian operator, that's the series of operations that we're going to apply to this thing called the wave function, that'll give you back your energy of your atom. So we talked about what the Hamiltonian operator is. It's the series of operations which, when applied to the wave function, gives the allowed energies of the wave function. What is the wave function itself? It's a mathematical description of the electron's matter wave. So if we have the wave function, we can calculate the energy of the atom. And that's kind of cool. But just like the Bohr model, it's also nice to know where the electron is, not only what its energy is. So in chemistry, we don't call it the wave function of the electron, we call it the orbital. And the orbital is effectively the region of space where we're going to find the electron. Orbitals are not related to the orbit of the Bohr model. An orbit is a circular path, whereas an orbital is a description of the matter wave of the electron. So we talked about the Hamiltonian operator and calculating the energy of the electron. What's also cool is if you take the wave function and you square it, you get the probability density of the electron about the nucleus. And the probability density represents the number of electrons that you're going to find in a given volume. And that's kind of interesting. Well, what would be really interesting to have would be, just like in the Bohr model, is where we might find the electron with respect to distance. Well, we somehow moved forward. Distance from the nucleus. And it turns out we can take the square of the wave function and do some really simple math on it and get what we call the radial probability distribution function, which is the probability of finding an electron at a given distance from the nucleus. So this is for the n equals 1 state of the hydrogen atom. And so what we've got here is distance on the bottom and then the probability of finding the electron at a particular distance. And what you see according to the Schrödinger model is there's a very small chance of finding it a long way from the nucleus, a very small chance of finding it very close to the nucleus, and this is what we call the most probable distance. So most of the time you're going to find it right at that distance there. So the Schrödinger equation predicts that the electron in the ground state of the hydrogen atom will most likely be on the surface of a sphere. Okay, and if we contrast that to the Bohr model, what the Bohr model predicts is that the most likely place or the only place that you will find the electron is on an orbit with this radius. The Schrödinger equation says that you're most likely going to find the electron on the surface of a sphere that has the same radius as predicted by Bohr, but sometimes it's a little closer and sometimes it's a little further away. So it's got a little bit more fuzziness to it to reflect the wave characteristics of the electron. Now, what we've got here is what happens when we go to higher values of n. So previously we were looking at the ground state of the hydrogen atom, n equals 1. Now we're looking at n equals 2 and n equals 3. So what we see is this is the most probable distance for n equals 2. This is the most probable distance for n equals 3. And as we increase the n value, sure enough, the electron is found further away from the nucleus. But what is also interesting is that there are these positions where we never find the electron. There are some distances where the electron has 0 probability of being found. And also we see that there are these places on these curves where that are closer to the nucleus, where there's quite a high probability of finding the electron. So as we move away from the nucleus, the shapes of these radial probability curves get more and more complicated. So in the Schrödinger model, an electron's orbital is described by 3 quantum numbers. And if we compare that to the Bohr model, we only had the 1 quantum number, which was n. n equals 1, 2, 3, 4, etc. was enough to account for the energy levels of the hydrogen atom. In the Schrödinger model, we still have n, but now we have two other quantum numbers. N, just like in the Bohr model, can take on values 1, 2, 3, 4, etc. This is referred to as the principal quantum number. L is what's referred to as the angular momentum quantum number, and it's an integer that runs from 0 up to n minus 1. So if n equals 2, possible values for L would be 0 and 1. ML is what's referred to as the magnetic quantum number, and it's an integer that runs from minus L all the way up to plus L. So if L equaled 1, then ML equals minus 1, 0, and plus 1. So a valid orbital will have values for these quantum numbers that make sense. So we might have something like n equals 1, L equals 0, ML equals 0. That would be a valid set of quantum numbers and would describe one orbital. So, Louis de Broglie developed the first wave model of matter and described an equation for calculating the wavelength of a particle. Erwin Schrödinger extended this wave model to explain the energy of electrons, and for the first time, the energy of electrons in multi-electron atoms. This model is a lot more complex than the Bohr model, and it requires 3 quantum numbers in order to describe the location of the electron, whereas the Bohr model only required the 1.